Okay, so in the previous class, I think we were uh, discussing about the concepts, based on the offset voltages, right? Input and offset, input and output offset voltages. Just to recall, can you tell me what is this offset voltage? And does it really play a major role in manipulating the values inside the operational amplifier? Yes. Can I have some responses? So does it have an impact? These offset voltages, do they have an impact is my question. Yes, they do have an impact. Okay, fine. Now, if you can recall this equation, okay, because of this change in voltages, what happened? We are not getting the proper voltage, right, at the output side. We should be getting about 1 volt, but then we're getting, the difference between both of the input terminals. So this should not happen, right? Okay, fine. So continuing with our discussion, today we will be looking into the input bias current effects, just like how we saw voltages, okay, just like how these voltages, these input voltages, okay. Let us take this, for example, where my input offset voltage is VB2 minus VB1. So the voltages between the base of both the transistors. Now, what is this base that I'm talking about? This base, okay, the base of transistor Q1 and the base of transistor Q2. So VBE, the voltage between the base and the emitter of transistor 1. Similarly, VBE2, which means the voltage between the base and emitter of transistor 2, right? So let's get back to this equation here. We see that this input voltage is actually the differences between these two voltages, which is VB1 and VB2. Okay, so we had assumed that, if one is about 0.7 and the other one is about 0.69, just about 0.10 difference. Okay, so how it can play an impact? Okay, so minus 10 millivolt was the difference, but still we were able to find out that, because of that difference, our output is actually adding with the offset. The final output is actually adding with the offset voltages. Okay, and this offset voltage is nothing but minus 10 millivolt, which we saw previously, right? Because the same thing will be reflected at the output as well. So ultimately it is not giving us a proper 1 volt, but then it's giving us 990 millivolts. So with this concept, students, are you all clear, or any doubt do you have up till this point?
Clear, sir.
Clear? Okay, because see, why I'm asking you repeatedly is because, whatever concepts that we are learning keeps building up. Okay, so unless and until you have not understood, there's no point in me proceeding with the higher level concepts, right? Hope you're understanding what I'm trying to say, right? So are you all clear as to why we are getting this 990 and what is the impact of input and output offset voltages? Are you all clear?
Yes, sir.
Fine. Thank you, students, for your response. Now, moving forward, okay, we had just seen the voltages, right? Now we are going to see how currents can impact. Okay. Now, when we look at this table, okay, there is something called input bias current. Now again, this is some part of the portion that I have taken up from, you know, the data sheet of OPAMP. Okay, so I wanted to highlight this input bias current here. Okay, I hope all of you are able to see this input bias current, right? Okay. I think this should be easy for you, right? So here, when we talk about this input bias current, now we have spoken previously about the voltages, right? And now we will talk about the bias currents. So you can see that typically it's about 80 nanoamps, and it can reach to levels of about 500 nanoamperes. So having this sort of currents can actually impact. Okay, how can it impact? It can impact the drop across the resistances. Can you please name what kind of resistances are available in a transistor? Yes, Bikram, can you please answer that? Bikram, you're there? Kevin, would you like to take up that question? What are the resistances available in an OPAMP? Kevin, yeah, go on. Mansoor? Maurya? Maurya Nikhil? Anybody wants to take up that question? What are the resistances available in an OPAMP? Bhumika?
Sir, RC,
Yes, that's it. We have resistances.
RA, RB.
Correct. That's all. So the general resistances are across the capacitor and the emitter, right? Thank you. So due to these currents, what can happen is, due to this bias currents, there can be drop across these resistors. Okay, fine. The data sheet lists the maximum input bias current as 500 nanoamps. It's referring to IB1 and IB2. Now, what is this IB1 and IB2? What is it referring to? The base currents of both the transistors. Now, remember, I showed you two transistors, Q1 and Q2, right? So the currents across the base of these transistors are respectively called IB1 and IB2. Okay, so IB1 is referring to Q1 and IB2 is referring to Q2. So I hope there's no doubt with this slide. Is it?
Yes, sir.
Okay. Right. From the data sheets, we see that input bias current levels are ranging from about 0.8 nanoamps. Okay, now here again, I am referring to other transistors. Okay, other values, which is actually not required, but then this is only for your understanding purpose. Okay, so it's about 0.8 nanoamps for the model LM 108. It is just like 7404. Okay, 7408, 7400. So similarly, we have a model which is LM108. So here, we can see that it's about 0.8 nanoamps. Okay. And then about 50 picoamps for, LF353. This I have just put up here so that this will give you an idea that, each IC or each transistor, each different configuration or a circuitry will have certain amount of currents. So these bias currents. Now this LM108 is actually a BJT, sorry, input OPAMP. Okay, and your LF353 is an FET based. FET is field effect transistors, and this is bipolar junction transistor, BJT and FET. Okay, fine. The input bias currents have no effect on simple voltage follower circuit. However, they produce voltage drop across resistors, right? So this is what I'm referring to. I'm referring to this voltage drop which is happening across the terminals, right? Now, why is this voltage drop happening? It's because it is currents, right? There is small amount of currents. We saw that we have about 500 nanoamps, right? So these currents can actually drop across the resistor. Voltage drops are unequal. The difference behaves like another input offset voltage. So now we have another problem, right? Not only having the voltage, not only having the current drops, but then if these resistances are different, okay, then what is going to happen? If the resistances are different, the flow of these electrons are also going to get affected, which means the drop across these resistances also will change. Do you all agree with this? Now let us take, let's go back to the circuit, right? And we will assume that, we have certain amount of resistance here and certain amount of resistance here. Okay, so if these resistances, usually, transistors will have its own input resistance. Okay, let me show that probably in another slide where I have put it up exclusively. Yeah, here it is. So if these resistances are not equal, okay, so I am talking about, now this R2 and R3 becomes in parallel, right? Voltage divider concept. And I will put this form of resistance here. Okay, now this is the resistance that I'm talking about. So this resistance here, number one, and this resistance here, which is R1, should be equal. Okay, why should it be equal? Because whatever currents that are flowing through should have equal drops. If there is no equal drops, then what is going to happen? There is going to be a voltage difference. Now, if there is a voltage difference, then what is going to happen? Are we going to get zero voltage at the output, students? When is the case that we are going to get zero voltage at the output? Only when
there is no potential difference.
Not only no potential difference, both the potentials should be same, right?
Yes.
Both the potentials at this non-inverting terminal and the potential at this inverting terminal. If both the potentials are same, because they are equal and opposite, so what happens? They cancel out each other and there is not going to be any difference across the output, right? So this is actually an ideal op-amp, but practically this doesn't happen, right? So that's why even though there is currents, okay, there is different amount of currents that is happening, okay, because of which there can be drops across the resistance. Okay, right. Now moving on with the input bias current effects, let us consider this circuit here. Okay, so we have this circuit where it's actually non-inverting configuration. Okay, we have seen this this section, okay, very much, right? This part of the circuit very much, right? We have seen that previously for solving problems, and various things as that sort, right? Okay. So this part of the circuit is very much known to us, right? So the one, okay, which is on the right hand side, okay, is what we are going to deal with newly. Okay, this is what is a new circuit that we are going to deal newly. Right. Now let's concentrate on the one which is on the left hand side, okay, the green colored circuit, right? So we see here that the input voltage is VI, and it has a resistance R1, okay, and this is now connected across the non-inverting terminal. It has plus VCC and minus VEE, as we all know. It has a voltage divider circuit, which is R2 and R3. Now, what I'm trying to do is, I'm trying to get these transistors, okay, these resistors, which are in parallel, and I'm trying to bring it up here in my next circuit, okay. So you can see that your R2 and R3 are parallel to each other, right? And I should be able to put the formula, okay, R2 into R3 divided by R2 plus R3. So I should be able to put that formula and get an equivalent resistance here, right? Okay. Consider the non-inverting amplifier as in the figure. The resistance is in series with non-inverting input terminal is R1. So this resistance is in series with this non-inverting terminal, right? And that is in series with the non-inverting terminal is R2 is in parallel with R3, right? R2, R3. When R2 and R2 parallel with R3 equals R1, now not only the voltages, okay, but even these, these resistances also should be same. Now, why is it so that these resistances are to be same? Why do you think so? Resistances are to be same? Because what can happen if there is a mismatch in these resistances?
Sir, both inverting and non-inverting should have the same voltages.
Correct.
Just the sign should be different. If not, if resistance are different
Correct.
value of voltage will enter.
Very true. So which means we are not attaining zero output voltage, right? So different, thank you. So different resistances can actually cause different currents to get dropped across them. So if there are some different currents here, what is going to happen? I cannot achieve zero output voltage. Very good. Okay. So there should be equidistant resistance in series with each OPAMP input terminal. So which means I should make sure that these resistances are equal. Okay. So this R1, whatever value of R1, let us say 5 kilo ohms, and this R2 parallel with R3 should also be 5 kilo ohms. I should not be having one 5 and the other one probably 8 kilo ohms. No, it doesn't work out that way, right? Both the resistances should be the same. Both the input, potentials that we are giving should also be the same. So basically, it's practically very hard to get, these kind of conditions. So that's why, we are learning about these bias currents, what can happen if there is mismatch. Okay, so that's the importance. Fine. The resistance is seen looking out of each terminal should be equal. Now this is important, okay? And I want all of you to make note of this. Resistances seen looking out of each terminal should be equal, okay? So both of these resistances should be the same. Now there is a small catch here, okay? Even when equal value resistances are used, the resistance tolerance may be yet another source of input offset voltage. Now, what is a resistance tolerance? I think in your labs, you would have seen this exclusively, resistance tolerance. There's a separate section for it. Can you recall? What is this resistance tolerance? Yes. Resistance tolerance. You remember?
Sir, is it about
Yeah.
the maximum voltage a resistor can tolerate, or?
It is like, you will have something at the extreme right hand side, there's a small band, the BB Roy color coding, you will have plus or minus 5%, plus or minus 10%, gold, silver, all this. Do you remember now? Can you all
Yes,
recall?
sir.
Yeah, yes, sir.
Yeah. So this is nothing but called the resistor, the tolerance. Okay. Tolerance means it can go plus 10% above that value, or probably minus 10% above. So that's why, you have that plus or minus based on the color coding, right? So now there is another problem for us. What problem is it? Not only maintaining same resistances, but we should also maintain the same type of tolerance. Okay. So there should be a gold band on the top one, and at the bottom one here also, I should have a gold band, right? So same level of tolerances also should be maintained. So ultimately, I am just talking of an exact replica of the same transistor, of the same resistor, of the same voltage supply, okay, of the same wire, okay, right? So moving on, the voltage levels involved are easily determined by first calculating the maximum and minimum values of the resistances. So first what I will do, I will take that tolerance into consideration. Let's say it's about 2 kilo ohms, and the tolerance, say it is, it is probably 0.1. So I will add that 0.1, and then it becomes 2.1, and then I will minus 1, it becomes 1.9, right? So 1.9 to 2.1 is my range, right? So I will calculate the voltage levels or the drops across, okay, having these maximum and minimum values of the resistances, okay? So after doing that, okay, then I will get to know, or then I can actually calculate how much should I average the values, okay? See, it is just like this. Maybe in subject 1 you get 90, in subject 2 you get 100, in subject 3 maybe you get 99. And how do you take an average? You add them all, and then you divide by the number of subjects, right? Similarly here, what I will do is I will try to find out the worst case, the best case, and then probably try to bring them in a mid-range. Okay, so that is my idea here. So I hope this concept here is understood, right? The main thing that you have to understand is that you should not have resistances of different values. It should be of the same value, so that the current drop across them also will be the same. The input potentials, the input voltages that you're giving should also be the same. So this is the basic idea, right? Okay. So moving on, we will probably solve a example, okay, and then you will be able to understand as to how is the impact of these input bias current effects. Okay, so we have a non-inverting amplifier circuit, okay, as shown in figure A. Okay, so I have just brought it here so that it becomes easy for you. So this uses a 741 OPAMP, where I have R1, R3 is 2.2K, and R2, this one is about 220K. Okay. Determine the maximum possible output offset voltage. Okay, so which means I am talking about offset voltage, that is the output. So V naught OS is what is asked here, right? Determine the maximum possible output offset voltage due to, number one, the specified input offset voltage and the input bias current. So two things they want us to consider while finding out the V naught OS. So what is it? They want to keep this offset voltage into consideration and the bias current into consideration. Okay, so what you can do right now is quickly, okay, you can look at the circuit and probably draw it, and you can put these resistor values, okay, respectively on top, where it says R1, you can put 2.2K, okay, and similarly for R3 also the same value, and R2, so that it becomes easy for us to continue with our problem. So I hope all of you have this circuit with you right now, right? So we will start solving this problem, and we will try and understand the cases as to how this bias current plays an important role. Okay, fine. So we need some data here, okay, and from the data sheet, okay, from the data sheet, this is not given. Okay, the 5 millivolt is not given, okay, which is input offset voltage. So this kind of data will be probably given in the question, or sometimes it will be told to assume. Okay, so as I always tell you, the first thing that you can do is write down the formula. Okay, and this is our final formula, which is V naught. They're telling us to find out the output voltage, which is offset. Okay, and that is equal to your gain, which is ACL, which is closed loop, okay, and input offset voltage, right? So ultimately, even this is also a voltage, but then input voltage along with the gain. Right? So I find out that my ACL, I know we have seen the formula, right, previously, R2 plus R3 divided by R3. So that's the ACL, and I get the value about 101. Okay, both are in kilo ohms, the numerator and denominator, so it's just a number here, right? So V naught is equal to ACL, which is 101 into VIOS, which is 5 millivolts. So I multiply both of them, so I get about 505 millivolts. So in the question, A was asked the specified input offset voltage and the input bias current. So in order to know the input offset voltage, right, we need to know what kind of minimum value, the maximum value that we are going to give at VI. Okay, right. Now, again, from the data sheet, we try to understand that IB, which is the base current, is about 500 nano. Where did we find it? We found it here, right? We found it here, that the input bias current is about 500. Always we don't take the regular value, the general value. We try to take the maximum or the worst case scenario, okay, because whenever you're designing, you need to know the worst case analysis, right? So we know that IB is about 500 nanoamps, right? And then we're taking R2, R3 in parallel, and we're getting about 1.98 kilo ohms. I think all of you know the formula, right? I don't have to stress on it. Now the input resistance difference. Now we are trying to find out the difference between the input resistances. So that is nothing but R1 minus R2 in parallel with R3. Now let's go back here. R1 minus R2 in parallel with R3. So we are trying to find out the difference between these two resistances. Ideally, they should be the same, but practically it is a challenging one, right? So R1 is actually 2.2 and this is about 1.98. So we get about 220 ohms of difference. Okay. Now keeping this in mind, okay, we try to calculate the changed OS, okay, the changed input offset voltage. Okay, so IB, V is nothing but V is I into R. So R, the new R is 220, and we know that IB is about 500 nano, multiply both. So I am getting about 110 microvolts. So this is the level of current that is at the level of voltage that is getting changed just because of the difference in the resistances here. Okay, so what is the difference in resistances here? It is nothing but between R1 and the one which is in parallel combination, R2 in parallel with R3. So just because of this, okay, I'm getting some resistance, and because of that resistance, I'm getting a changed potential. Okay, I'm getting a changed potential of about 110 microvolts, even though it's in micro, but then it still matters. It is not zero. Now we will be calculating for this updated VIOS. So I'm going to substitute this. Okay, previously we had substituted 5 for VIOS, right? So now we're going to calculate the output. So output is ACL into VIOS. So ACL, we all know it's about 101. We take the same value here and put it, right? And yeah, that's the same value. And we're going to take this 110, okay, here. So ultimately, I am now getting to know that the final value is about 11.1 millivolts difference. Okay, so you can just compare. Okay, you can just see that, here I'm getting about 505 millivolts, but then here I'm getting about 11.1 millivolts. Okay, so there's a huge difference. And why is this difference? This difference is happening just because of the resistances, the value, the change in the value of these resistances. So I think you're all able to understand the impact because of the change in resistance. Is it? Yes or no?
Yes, sir.
Yeah. So just try to compare, this value and this value. Okay, that's why it says V naught OS A, which means offset voltage for output. Okay, and this is the first case, and B is talking to us about the other case where we have found out the updated values. Okay, so is this problem clear, students? What are we trying to learn in this problem? We are trying to learn that just because of the change in differences in the resistance, there can be change of output voltages. So what are these resistances that I'm talking to you about? The resistances are nothing but the one that we just drew. Okay, if there is a change in this resistance, okay, and the resistance which is below. Okay, so I'm talking of this and this. So if both of these resistances are different, then it's going to have a major impact. Okay, my output voltage is also going to change. So internally voltages are affected, then the currents are affected, the drop across resistances are affected, and ultimately my final output voltage will also change logically. Right? Moving on to the next concept is about input offset current. Okay, input offset current. The previous one that we saw was input bias current. Okay, and now this is input offset current. So we saw input offset voltage, right? Remember, we had about 7 and then 6.9, right? So just try to recall this, which we saw at the start. Yeah. So these are nothing but offset voltages. Okay, now we're going to learn about offset currents. Okay, input offset current. Another result of input transistors of an OPAMP not being perfectly matched is that, as well as the input transistor base emitter voltages being unequal. So what is this base emitter voltages? VBE. Okay, the gain which you see in the current, okay, of one transistor may not be exactly equal to that of the other. So why is it so? Why is the gain changing? Because of the difference in voltages, because of the difference in resistances, because of the change in drop across these resistances. So because of which we will be able to see that even the gains are different. Okay, Q1 gives us different gain and Q2 gives us different gain when I try to calculate it as an individual transistor. Okay, taking Q1 separately. Okay, let me just take you back and show you these transistors. Yeah, Now let's say, for example, I just want to find out the gain of this transistor. So how will I find out? I will be calculating what is my output. I will see what is my input. Output by input is anyway going to give my gain. So similarly, I'm going to calculate the gain of the other transistor as well. And I'll be able to, conclude that both the gains are different. Okay, that is because of various factors which we saw. It can be input offset voltage, it can be input bias current, it can be the differences in the resistances. So all these can actually impact the level of output voltage. Okay, so thus when both transistors have equal levels of collector currents, which is IC, their base currents may be unequal. So even though their ICs, IC1 and IC2, IC1 is equal to IC2, even though we satisfy that case, IB1 will not be equal to IB2. Okay, so the difference in two input current levels is known as input offset current. Okay, so this will be asked in your examination. What is meant by input offset current? Okay, so what is it? The difference in two input current levels is known as input offset current. Okay, offset means it is going somewhere else. Okay, it is not as per the standard. So offset means some other level. Okay, therefore even when equal value resistances are connected in series to the input terminals, the input offset currents produces unequal voltage drop across the resistance, right? So because of these resistances, so there can be different drops and ultimately different currents. The difference in resistor voltage drop behaves as another input offset voltage. So again, it is backfiring. How is it backfiring? Because of different levels of resistors, the voltage levels also does change. So the maximum input offset current for 741 OPAMP is specified as about 200 nanoamps. Okay, so this is also from the data sheet. So ultimately, data sheet is very important, where we get to know how much is the value of input bias current. We get to know, what is the levels of output offset voltage, in what temperature I should operate. Do you think operating in all temperatures gives us all ideal outputs, students? Let us say I'm operating the IC at say 25 degrees centigrades. Okay, and then I calculate the output. Then I go to another room. Okay, and probably let us assume that it is about 50 degrees centigrades, and then I calculate the output. So do you think both of the outputs are going to be the same, or is there going to be any impact because of the room temperature?
Output will be different, sir.
Output will surely be different, right? Correct. So that is because of this temperature. Temperature can also accelerate the flow of electrons. Okay, you should go back to physics. So in physics, it says that temperature can also assist in conduction, right? Heat is also a form of energy. Light is a form of energy, right? So all these can impact the way in which your electrons can travel. Okay. Now moving on to the next topic, the next subtopic, okay, which is combined effect of input error sources. So it can be because of the voltages, it can be because of the currents, it can be because of the bias, it can be because of the resistances. So all together, okay, it is called combined. In some cases, the polarities of various sources of input offset may be such that they partially cancel each other. So just because we have this plus and minus, so a plus 5 minus 5, ideally there shouldn't be any sort of difference. But then instead of maintaining plus 5 at one terminal, if I'm maintaining even plus 5.1, then there is going to be the difference between terminal 1 and 2, that is inverting and non-inverting these differences are again taken and it is amplified because the gain is infinity, right? So which means, by having it in the negative feedback mode, I will try to bring down the oscillations. Once the oscillations are down, my outputs are going to be a little stable compared to the positive feedback. Alternatively, it could also be that they all produce output offset voltages with the same polarity. Okay, normally this worst case has to be assumed. So I want you to please take note of this. Okay, even though we are thinking of canceling out of the voltages, but the worst case that we have to take is this. Okay, that they produce output offset voltages with the same polarity. So we should think that the levels or the errors are higher than canceling out each other. So students, you're able to understand what I'm trying to say here?
Yes, sir.
Instead of assuming that these voltages are getting cancelled out, we should assume that they're getting added and the error is getting bigger. Okay, that's what it's trying to say in simple words. Okay, now let's continue with the solving of problem. Okay, so in the previous one we had solved A and B, right? A and B was talking to us about finding out the normal offset voltage and the input bias current. So this input bias current, how we found out? We found out because of the change in the resistance. This was the key formula for us, right? R1 minus R2 in parallel with R3. So this was the key formula for us. So keeping this key difference, okay, we recalculated what is going to be my input offset voltage, and ultimately because of my input offset voltage, I'm going to change the output offset voltage because that is nothing but ACL, which is gain into input offset voltage. Right, now continuing the same problem, okay, having the same circuit, the same resistance values, and having to know the value of V naught OS A and V naught OS B. Okay, we will continue with the C problem. Okay, the input offset current. Okay, so they want us to calculate the input offset current, the resistance tolerance. Now remember, I was talking to you about the tolerance plus or minus some percentage, so we have to take that also into consideration. Then all error sources. Okay, so what all can actually be a reason for error? So which means we have seen input offset voltage, output offset voltage, input bias current, input offset currents. So all these will be taken into consideration, added up, and we can finally conclude that how much of error is going to happen, right? Okay, so for this, okay, for input offset current, now remember we had seen that it's about 200 nanoamps. Remember, I had put it up here. The maximum input offset current is about 200 nanoamps. So taking this number here into the problem, so we know that it's about 200 nanoamps. Okay, the maximum, I'm always considering the worst case, right? So I'm calculating now the input offset voltage. So V is IR. So I already have here R. I'm taking the value R1 was about 2.2 kilo ohms. Is it? Was R1 2.2 kilo ohms? Right? So it is 2.2 kilo ohms. So taking those same configuration sets, okay, so I find out that my input offset voltage is about 440 microvolts. So now I know what is the input offset voltage. So I will be able to find out the output offset voltage. So output is nothing but gain into input. So gain we calculated as 101 into this new offset voltage. So I'll be getting about 44 millivolts. Now let us assume that your R1 has a tolerance of plus 10%. Okay, so if I take 10% of this, okay, so So, I should be getting about 22, right? I should be getting about 22. So I'm adding this to 0.2. Okay. So it should be giving me about 2.42 kilo ohms. Then if I take 10% of this, so it should be somewhere point 20 or something as that sort. Okay, yeah. So once I minus, okay, it's going to be about 1.78. So minus 0.20, right? So 10%. So I am taking the tolerances here into consideration. So in one case I'm taking plus and the other one I'm taking minus. Okay, so because it's plus or minus 10%, right? And R1 is connected at the non-inverting, and R2 in parallel with R3 is connecting to the inverting. So plus 10, minus 10. So plus or minus, both are taken into consideration, right? And now I recalculate my input offset voltage. So we know that IB, V is equal to I into R. So I into R is nothing but R1 minus this one, which is equal to IB. We had found out that it's about 500 nanoamps, right? 500 into R1, we have the value here. The new value I'm bringing down here, minus R2 in parallel with R3. So I have about 1.78 kilo ohms. So taking this new values, I will be getting 320 microvolts. Okay. So now since I have updated input, I am also going to get the updated output. So output is nothing but ACL into input. So ACL is constant, which is about 101. And this 320, I'm bringing it down. So I am going to get my updated output offset voltage. Now, here he has asked us to calculate all the error sources, right? So I calculate the all offset output voltages for A, B, C, D. Okay, so all these differences, okay, all these differences in output voltage, and in the previous one we had got 505 and then 11.1, then you can see this 44.4, right? You can see this 44.4, right? And then you have 32.3. So taking all this, okay, you will be getting about 593 millivolts. Okay, so what did we do in this problem? We ultimately found out what is my input offset current. So how do I get that value? From the data sheet. Once I have the current, okay, if I multiply with the resistance, then I'm going to get the voltage. Once I have the input voltage, see only three formulas. V is equal to IR is the standard formula that we are going to use. And then we're going to use V is equal to V naught is equal to ACL into VIOS. If you can just see, we have used this formula many times. This formula we have used many times. Yes or no? So knowing this formula is important. Okay. And just substituting, and based on the question asked, based on the tolerances, see the tolerance is given plus or minus 10%. So we get plus 10 and minus 10, and ultimately my V is I into R. Once I get input, see again the same formula is repeated here. Okay, I get the output, and this maximum, okay, the maximum is nothing but the addition of all that we had done previously. So it becomes an addition of all that we did previously, and finally we get the value, okay, which is about 593 millivolts. So students, any doubts here as to how these problems are solved, or what are we trying to see or look into these problems? Are you all able to follow? Are you all able to understand the impact of errors that can happen? Yes, can I have a response?
Yes, sir.
Okay. So today what I'll be doing is I'll be sharing these, this document with all of you so that you can start practicing them, and you will get a feel as to how these formulas are put up, and how it is solved, because attending the class is important. Okay, see, I will tell you the importance to deliver, okay, this lecture. I would probably refer about 7 to 8 textbooks. Okay, and it's when we present, it becomes an easy task for you, because you don't have to go through all the 7 to 8 textbooks. Okay, and going through the notes again, it becomes very simple for you to understand the impact of a certain topic. Okay, so that's the reason I'm asking you, if you're able to follow. If you're not able to follow, then feel free to ask questions so that I can always get back. So is it clear, students? Can we proceed with the next topic?
Yes, sir.
Okay, fine. Thank you for the confirmation. Okay. Now, in order to nullify all these issues, okay, there's a smart method that scientists or electronic engineers have come out with. Okay, even though the circuit looks so simple, okay, but then there's a huge impact that can happen just because of all these offsets. So when I say offsets, there are there are input offset voltages, there are output offset voltages, offsets due to the currents, right? So all this can be nullified with the help of this circuit. Okay, so you can see that there's a small resistor Rp that is connected between both the transistors Q1 and Q2. Now this is nothing but acting like a potentiometer. I think you guys have used it in the experiments, right? Potentiometer. How many of you have utilized in your practicals? You've seen it, right? Practically, how this potentiometer works.
Yes, sir.
Yeah, it has a variable resistance. Correct. So because of this variable resistance, we can either upscale or we can downscale, right? So this is a very smart method of getting the errors nullified. So we'll just look into it. And for today's lecture, this is going to be our last concept. Okay, how do we nullify all the errors which we spoke about previously, just with the help of these simple resistor, which is Rp. This method deals with the input offset voltage and current. So using this method, I can actually deal with whatever voltages were getting offsetted, and the currents as well. So it is a resistance potentiometer Rp connected at the emitters of the input transistors Q1 and Q2. So Q1, Q2 emitters, and the resistor here Rp. Adjustment of Rp alters the total voltage drop from each base to the common point at the potentiometer moving contact. Okay, so if I increase, if in case there is a lot of input offset voltage, then probably I can increase the resistance, due to which there can be a huge drop. Okay, if there is too less, then I can probably decrease my resistance. So that's the whole idea. This adjustment can null the effects of all sources of input offset voltage. Okay, so very important concept where you can nullify, okay, you can nullify all the errors just because of Rp. Okay. Now in this figure here, okay, you can see that how it is connected. You can see that it's connected. Let's take 10 kilo ohms as example, and it's connected between terminal 1 and 5, and the Okay, the adjust, you can see that there is an arrow here, which means it's variable. So this is connected to the negative terminal, minus VEE. Okay. So a 10 kilo ohm potentiometer is connected to offset nulling terminals, which is 1 and 5. And its moving contact is connected to the negative supply line, which is minus VEE. Okay. So this is a very important piece of hardware, okay, which helps us in finding out or nullifying the offsets. The potentiometer is adjusted to null the output offset voltage to 0. So using this, I can actually make my output voltages to 0. Okay, isn't that great? Even though we are dealing with a lot of resistances, change in resistance, change in IB1, IB2, okay, because of which there can be a lot of drops in these resistances. So the levels of currents change. So the input offset currents, the input offset voltages, all these are changing. But just with the help of this, I can probably call it as a wonder circuit. Okay, we are able to rectify or nullify the previous errors, right? So the input offset adjustment is listed as plus or minus 15 millivolt in the data sheet. So that's the range that has been followed. Okay, it's about plus or minus 15 millivolts. So just because of this, I will be able to nullify whatever error is coming across my output. Okay, so I think you all have understood the concepts involving offset with respect to voltages and currents. Is that clear, students, with all the concepts that we studied so far?
Yes, sir.
Yeah, okay. So ultimately, we are trying to have a system which helps us in nullifying the errors. Okay, we should not have any errors. Okay, we should make sure that both the transistors are either manufactured in the same way or the components used are made the same. When I say components made the same, it means same resistances, same input voltages. Okay, so this can actually impact the way in which currents drops across the resistance. So I think we will end our session here. Okay, and we will continue with the next topic. Okay, so we have dealt together offset voltages and currents. In our upcoming class, okay, we'll be learning about the impedances. Okay, just like how we saw the offset voltages and currents, we'll be learning about input and output impedances, how this impedance can impact the OPAMP. Okay.